frequencies. Yeah. All right. Yeah, so now, when we process the digital signals, yeah, because it's not the analog functions. Here, what do we have? Digital signals, a sequence of numbers. Yeah, that's our, digital signals. All right. Yeah. Then, when we apply here discrete Fourier transform, yeah, we get a spectrum, frequency spectrum. Yeah. So we have formulas. Okay, the formula is like this. Yeah, the matrix form. You multiply big Fn, F sub n matrix, n by n matrix. All right. All right. Yeah. So that matrix, we need to use this little w, the entry, yeah, inside that matrix. We use little w. Yeah. So Fn equals, so use that w, each entry, row number n, column number k. So you take the, power function, yeah, w to this number. So yeah, that's your matrix entries. So then you multiply the given f vector. So you get the discrete Fourier transform. But the question here is, we want to, so here, yeah, because this is a practical question, especially for us. Yeah, yeah, because you will be engineers. For engineering people, you need to provide good solution in the real world. Yeah. When you do computation like this in the real world, a very important consideration is performance, how fast you can do. If it's very slow, then your solution, although it is correct, but your solution is not good because it's too slow. People cannot wait. Okay? So here, now, we need to find much faster computation algorithms. So here, it's an algorithm issue. Yeah, our goal, we just do this. Okay, now that formula, that's the result. But how do you do it, right? You have many different ways to do that multiplication. The question, can you find the fastest way to do multiplication? That's important. All right, yeah. So here, yeah, we call the component. So each f hat n, yeah, we call the component, yeah, in our discussion. Yeah. So our frequency spectrum. So each, that number, it's a component after we do the Fourier transform. Yeah. All right. So here, there is a concept called the resolution of 2 pi periodic function of x. So here, this resolution, it means this. The resolution is the smallest non-zero distance between adjacent values. Here, the smallest, two adjacent. You look at two adjacent, non-zero, okay? Yeah. Distance. Yeah. Yeah. So how small it is. Yeah. So that's the resolution. Yeah. Remember, we do equal space sampling, right? We do equal space sampling. Yeah. So that's the, smallest non-zero distance. Then there is an aliasing problem. Yeah. So in the real world applications, this aliasing problem could occur frequently. So we want to avoid aliasing. So what's that aliasing? The misidentification of a signal frequency introducing distortion or error. Yeah. Because when you calculate the frequency, yeah, so here, this side of frequency spectrum, okay? But in your calculation, due to some reason, you misidentification. What's your misidentification? You calculate the coefficient, but you put it in the wrong location. misidentification, right? So you mess up, okay? You mess up. Yeah. That could happen. That could happen in the real world. So here there is an example. You have that experience. In a motion picture, rotating wheels appear as rotating too slowly or even in wrong sense. Yeah, sometimes you watch the videos, the wheels turn opposite direction, right? Yeah, that's due to the aliasing, because the misidentification of the frequency. Yeah. Why? Because this resolution is too low. The resolution too low, yeah. Aliasing caused by sampling at too few points. If you add more points sampling, then you can eliminate aliasing. Yeah. Because you add more points, you can do the calculation more accurately, right? More accurate than less misidentification, right? Because you have more points. Yeah. So your answer will be more accurate. More accurate, then you eliminate misidentification. That's the aliasing problem. Okay, so you increase the resolution. You calculate, you add more points, that means you increase the resolution. Make a resolution higher, then your approximation better, then you can eliminate aliasing problem. Yeah. Yeah. So that's based on that, yeah, it tells us when we do the digital signal processing, we want to use sufficiently high resolution. Okay? Sufficiently high resolution. Yeah. So when we use the sufficiently high resolution, the n number relatively large, right? Yeah. If too small, then you have a lot of aliasing problem. Yeah. So you want to make that n not too small. Okay? Sufficiently large. Just large enough to eliminate aliasing, okay? Just large enough to eliminate aliasing, okay? All right. So then, when that number is large, do you need to do a lot of computation? Your computation time would be slower, right? Yeah? Yeah. Think about it. Well, you double the number, triple the number, then your computation time would be, more than double, right? Yeah. Could be squared. For example, if you double, your computation time could be 4 times. It's a square. If you triple the resolution, your computation time could be 9 times. Now, make your algorithm faster is more important. Yeah? Because otherwise, your computation too slow. Okay, all right. So after the break, when you come back, so then I talk about how to make it faster. How do we apply fast Fourier transform to make it much, much faster? Avoid aliasing by high resolution signals. Now, the reason why we want to, use that n number pretty high. Yeah. Yeah. So then the computation problem is important here. For high resolution signals, capital N is usually large in applications. Computation efficiencies. For each component, you need to calculate, apply this formula to calculate that F n hat. Yeah. All right. But if you calculate directly, if you cannot discover some efficient calculation, here you need to use this asymptotic notation. Do you know about this asymptotic notation? Big O of n multiplication of only when you take computer algorithms, we use this terminology. Yeah. So in computer algorithm, we call it asymptotic notations. Okay, several. So asymptotic notation. Okay. Here, big O represents. So here, I just give you the idea. You just imagine how large is that big O of n. you just imagine some constant c times n. Okay? Constant c, certain constant c. Could be 1, could be 3, you know. Yeah. Just the constant. After you select it, you know, that constant should be fixed. Then you can call it big O of n. Okay? A certain constant multiply n. So why constant? So here, let me explain why it's a constant. All right. Here, when you calculate x sub k, do you need to do multiplication here? Pi times t, constant, right? You know, one multiplication, right? You can treat multiplication. Division, we can also treat as multiplication, okay? 1/n times, so you can count. So 1, 2, 3, yeah. Here, do you need to do multiplication between fk and e, right? When you calculate multiplication, yeah. So you can count a few numbers. Then the total multiplication, that's that number multiply n, right? Yeah. Because for every term, you need to do that fixed number of multiplications. Yeah. For example, 4 or 5. That constant could be 4 or 5. Okay. Then the total multiplication could be 4n or 5n. Okay. 4n, 5n, but here, because we don't want to specify that constant, so we want to skip that constant. Okay. Yeah. If we skip constant, here we use big O of n, you don't see the constant. Yeah. Because the constant, we know, easy, so we don't want to, you know, look at it directly. Yeah. All right. So that's the, in computer algorithms, we use this notation, asymptotic notation. All right. So here, for each one, yeah, for one component, you need to do this many multiplication. But how many components do you need to calculate? N, capital N components, right? Look at how many components. You have total capital N components. Then, how many multiplications do you need to calculate? Yeah. Capital O of capital N squared. Capital N squared. Yeah. Because that's one. But now you have capital N. That many. So you have capital O of capital N squared. That many multiplications you need to do. Okay? Yeah. Is there a lot of multiplications? So in the real world applications, where capital N is relatively large, do you need to do a lot of multiplications like that? Right? Yeah. If you do that many, yeah, so many times it could be slow. Yeah. So here, let's get an idea. When n is 1,000, yeah. So your sampling rate, in one interval, you take 1,000 samples. That resolution. Yeah. If n is 1,000, then n squared is 1 million, right? 1 million. Okay. When you do the multiplication, you need to do some constant multiple of 1 million. Yeah. To be simple, let's just say 1 million multiplications. Okay. We need to do 1 million multiplications. Yeah. All right. Now, question: how to make the computation faster? No. Because when n equals 1,000, you need to do 1 million. If n is much more than 1,000, then this number grows much, much faster. You need to do a lot more multiplications. That could be very slow. Okay? When you do Fourier, discrete Fourier transform, it could be very slow. Okay? All right. Now, there is a very efficient algorithm called fast Fourier transform. Yeah. Because, the inventor discovered some nice property, so we can take advantage of the property to make it faster. Yeah. All right. Improvement. that algorithm can improve the efficiency from big O of n squared to big O of n log base 2 of n. That improvement. Okay? Here we still use the asymptotic notation, big O, but the question is, do you have an idea how much is the improvement? From big O of n squared to big O of n log n, how much is the improvement, right? What do you see? Just the formula. But if you just look at the formula, you do not have any impression, right? How good is the improvement? Yeah? If you just look at formula. Yeah. So here, let me show you, let you get some feeling, concrete feeling about the improvement. Calculate the improvement factor when our first calculation when n equals 1,000. How much is the improvement? When n equals 1,000, straightforward method, we can call it brute force method. Brute force method, we need to do n squared operation. And the fast Fourier transform, we do n times log base 2 of n. So after cancellation, the ratio of these two algorithms, n over log base 2 of n. Okay? How large is that? Yeah. Let's plug in 1,000. 1,000 over log base 2 of 1,000. Yeah. The numerator, we know 1,000 approximately equal to 2 to the 10th, right? Yeah. So in computer science, we know 2 to the 10th, very close to 1,024. Yeah. 2 to the 10th, we know this number equals 1,024. Yeah, that's close to 1,000. Okay, we just use as approximation. Okay, all right, 2 to the 10th. But after you take log base 2, the 2 is gone. You only have 10 left. 1,000 over 10, you get 100. So the ratio is 100 to 1. Is that improvement good? Yeah. So that means if you use the brute force method, for example, if you take this amount of time, if you use fast Fourier transform, you need a 100th, 1% of the time, only 100th. Okay, you only need 1% of the original time. You can get the same result. That's the power of fast Fourier transform. That's the power. Okay. 100 to 1 ratio improvement. That's for n equals 1,000 sampling rate. All right, second one. I want to show you another example. The second one, this time n equals 1 million. Very large, 1 million. Okay? This time, if we take log base 2 of 1 million, do you have an idea how much is log base 2 of 1 million? Idea? 2 to the power of what? 20. 20, because equals 2 to the 10th times 2 to the 10th. Each one is 1,000, right? Approximately 1,000 here. 1,000 times 1,000, you get 1 million. Okay? So 2 to the 20th, 1 million. Okay? 2 to the 20th. Now, log base 2 cancellation, this base 2 here, you get 20. 1 million over 20, you get 50,000. Now the ratio becomes 50,000. Okay? If the sampling rate is 1 million, huge sampling rate, then your improvement this big. 5,000, 50,000 to 1 ratio. Fast Fourier transform. So that's why this algorithm is so useful in real, software. So for signal processing, this algorithm must be in any software for signal processing. Fast Fourier transform. Yeah. All right. Yeah. Next slide, I want to talk about the idea. Yeah. How to get that fast. Okay. How can you get that fast? Yeah. Here, next slide, I talk about that property. Okay. I give you the property. Yeah. How to use the property to derive, that derivation. So I may use a 10-minute video to explain that part. So today, because I have 2 more questions I want to cover. Okay. All right. Property for computation efficiency. Yeah. When there are even number of samples. Here, in order to apply property, we need to assume there are even number of samples. If odd, we need to find a way to make it even. Yeah. Even, because even we can use symmetry. Odd, the symmetry not that convenient. Yeah. Even. So n equals to m, then little w, we have that, but this m, you can see m number is the 1/2 of the sample numbers. 1/2. Okay? So W capital M, yeah, so based on the definition, you can see the relationship between these two little w, Wn squared equals Wm. Yeah? That's simple. Yeah, because the square relationship. This is 2-to-1 ratio. Okay? Yeah. So the 1 n larger, so when we take square of the first one, we get a second one. Yeah. Simple. Okay? That's very straightforward. Yeah. All right. Yeah. Now, when we do calculation, here, let's look at the calculation. Okay? Now you can see we can split the samples, input signal samples, into 2 parts, even samples and odd samples. Yeah, even and odd, we split. Because when you split, you can see even samples share some property, odd samples share another property, so you can treat them, using some special properties. Yeah. So the signal, original signal, let's split into the even sample part, okay? Yeah. And odd sample part. Yeah. So same number. Yeah. We assume even, so they have the same number. Okay. Same number, so we can handle using some special way. Yeah. The Fourier matrix. Yeah, here we use the capital M. Yeah. Because capital M, we can apply on even sample vector, odd sample vector. Same dimension. Okay. Yeah. 1/2 of the original sample dimension. Yeah. All right. Then the even frequency spectrum vector can be calculated using this matrix. Odd frequency vector we can calculate using this matrix. The same FM matrix. Okay? Yeah. Then, after we get it even, odd, so we treat these 2 vectors temporary, intermediate vectors, because our destination frequency coefficients, we need to use these 2 vectors. Here, these 2 formulas. Use these two vectors. Yeah. These 2 vectors. Yeah. How do we get these formulas? We explore the property between even samples, odd samples. Yeah. When you write, the original formula, this original formula, if you write it out, then you put even terms in one group, all the terms in another group. Then you do factorization. Yeah, common factor you can factor out. You do factorization, then you can see this property. Same f capital M, you multiply these two vectors. Yeah. So then, after you calculate two vectors, you just do the calculation like this. You get, first half, second half. This is the first half. Yeah. Because m from 0 to m minus 1, the first half, then plus m, the second half. Yeah. So you get all the coefficients, all the coefficients for the frequency spectrum. Yeah. All right. All right. Yeah. So regarding the fast Fourier transform, at this point, we have derived main formulas, the basic formulas. So actually the derivation, So in class, I just gave you the formulas. But how to derive, how to apply these formulas, I didn't cover in class. Here, let me use, probably, I estimate about 30 minutes. So I will explain two things. First, how to derive these formulas. Second, how to apply these formulas in an efficient way. Yeah. Because although you have these formulas, but if you apply in a wrong way, you cannot save a lot of computation time. Yeah. So you have to apply it in the right way, in an efficient way. Yeah. So let me explain these two things here. Yeah. First, let's recall the formulas I gave you some time ago. Yeah. All right. First, the main discrete Fourier transform. So we start from there. The main discrete Fourier transform, the formula is this one. So that's the original discrete Fourier transform. We call it DFT. So this is the DFT formula. Okay? Yeah, the original. Yeah. All right. So then we represent this formula in a matrix form. So this is the matrix form. All right. We multiply this n by n matrix. So we call the Fourier matrix, n by n. And in order to get a frequency, so here we need to convert from sampling values from the time domain to frequency domain. Time domain to frequency domain. Yeah, so here, time domain, so we have samples. Yeah, the function represented in, sampling values. Yeah, transpose. So then so here, f we treat as a vector. F hat, so that's the, frequency equals the Fourier matrix, all right, capital N. Yeah, so here, the original. So here, look at the original number of samples, Fm. So not this Fm. Fm we cut in half. So f of m we will use it for fast Fourier transform. Yeah. So that's the version we need to use for fast Fourier transform. So the original is f capital N matrix times the sampling vector. The original function sampling vector. All right. So then, in order to support efficient computation, we assume the n value should be an even number, because even number we can split into two equal-sized vectors. Two equal-sized vectors, the first half, the second half. And for the second half, we can save a lot of computation because we can use the computation we did in the first half. That's the idea. So that's the reason we need to consider even number of sampling values. Yeah. All right. So then, these W, so here, the W, so the W definition, so you can see here, so we have, relationship, 2W, so one version for N, one version for M. Yeah. All right, so then, notation, because these two, the main formulas, the main formulas, and to understand the main formulas, all right, so look at the, frequency, so we call the frequency spectrum. So this, the vector, so so this is a component of the vector. So we'll put all the component in one vector we call the frequency spectrum. The frequency spectrum we split in even components and odd components. Even components we put in the vector, this FEV hat vector. Odd components we put in another vector, FOD hat vector. And the even one, we can use this expression. Odd one, we can use this expression. So next the question. First, because this formula I gave you before, but how to get them, right? Some of you may want to know. So here, I just assume some of you may like to know how to get these formulas. So in our textbook, this part, you may not be able to understand easily, because many steps are skipped. So many steps are skipped. How to get this expression, that expression, and this one and that one. So many intermediate steps are skipped. So here I recover those skipped steps to help you understand these formulas first. That's for the first part. Second part, then, for the efficient computation. All right, so let's look at the, how to see these formulas. All right, so now let me start. Before that, I just, explain the notations, formulas, and background. Try to recover some memory. So if you learned our old slides, so now because you need to get familiar with those old slides. When we start, this is, so here I do not use the summation, so I just write the expansion in this way, term by term, because in this way, when we do the manipulation, so you can see the details a little easier. Because if I use the summation notation, then it's too abstract. So you may feel very hard to understand. So here I use the explicit representation. All right. So in this, this is the, so here, why this is correct? Because this is the definition of the Fourier transform. Although definition, because remember this formula is derived, based on some computation. So certain computation.
So the textbook provides some details. Yeah. So that detail, I skip it. So here, we start from this formula. All right, so we assume it's correct. Yeah. So actually, there are many different ways we can see this formula. Although some basic formula computation, some basic formulas we need to use. Yeah. And that basic formula is given in the textbook. Yeah. All right. Here, I want to group all the terms into two subgroups. The first subgroup, this parenthesis, contains all the terms with even subscripts. So 0, 2, 4, n minus 2, yeah, because we know n is an even number. So n minus 2 also even number. Yeah. The first group, subgroup. Second subgroup, yeah, all the terms with all the subscripts. 1, 3, 5, and so on. Yeah. So then, when we group all those terms with all subscripts, there is a common factor we can factor out. Yeah. W sub n to the nth power, capital N sub capital N to the little nth power. Okay? Right? So that common factor can be factored out easily. Yeah. But after factorization, so you can see, if you compare the terms inside these two parentheses, you can see, for the corresponding terms, the W part, the power of W part, exactly the same. Yeah. This structure, we can represent this structure in a simplified way. Yeah. All right. So now, how to simplify? How to, make the expression simpler? Yeah. All right. First, we change. Yeah, because when you look at it, each W part. Remember, W sub n square equals Wn. Yeah. So now we can change to the base W sub n. M, capital M. All right? Yeah. So then we divide the exponent by 2. Yeah. So you can see we get the expression, but this time we use the W sub m sup multiple of little n. Okay? K multiple, so the general one we can assume K multiple of little n. Okay? Yeah. Yeah. Because if we use this new representation, then we can get a matrix expression. Yeah. Yeah. So you will see it. Yeah. Similarly, the other part, the other terms, if we do not look at the W term, W factor outside the parenthesis. Yeah. So if we do not look at that, inside the parenthesis, we have, similar expression. Now you can see these two parentheses, structure-wise, they are similar. Yeah. So only difference, we just replace odd even sampling values by odd sampling values. That's simple. Okay? All right. So then, after you understand this structure decomposition, now you can see another relationship. Yeah. All right. Because, so here we want to further simplify. further simplify the formula. Yeah. All right. So here, yeah, look at this formula. Now we want to understand this formula. Okay. Yeah. To understand this formula, look at the structure, look at the subscript. Little n, we only consider the range for the subscript little n in the first half, from 0 through capital M minus 1. We do not consider the second half, because second half, if we just use little m plus capital M, we can easily get a copy of second half. Yeah. In this way, in this understanding, we can save computation. Yeah. So if you ask me why we do this, because we want to save computation. Yeah. So when I go to the efficiency explanation, so you will see the structure helps us to save a lot of computation. Yeah. All right. Yeah. So now, here for the second half, yeah. So when little n greater or equal to m, that's the subscripts for the second half. Yeah. First half, based on our assumption, so we use the first formula. Yeah. The first formula, okay? Yeah. So, from this expression, you can see corresponding to the first formula. Yeah. But for the second half, now we need to do some further simplification. Yeah. Second half. Let's consider little n plus m. So here, actually, the little n, we should change the notation slightly. Here, I put a tilde. Because this little n, this tilde, is in this range. Is in that. The little n without tilde, that's in the range greater or second half, greater or equal to capital M. Yeah. So this variable is different from original little n. We want it in this range. Yeah. So here I use the little n. But why later in my official version I remove the little n? So remember, we remove the tilde sign, because the tilde, I mentioned a few times, the tilde, the slightly different notation, quite annoying, right? So when we represent it, it's quite annoying. Yeah. So here we use a method I call abuse the notation. So here we abuse the notation. We abuse that notation. Okay? Yeah. Yeah. All right. So we still we use that little n. Okay? Yeah. So we go back. Yeah. So we still use that little n. Okay? All right. So now let's look at the individual W factor. Okay, W factor. Yeah. So we can simplify. Yeah. Here. All right. So individual W factor. So here, that is this part. Individual W factor with n greater equal to capital N. Okay. So we want to further simplify all these factors. So here, how to simplify? We split into product of two W terms. Two W factors. Okay, all right. So when we split in this way, the first little n is in the range between 0, 1, capital M minus 1. Okay, yeah. The first. Yeah. And the second part, yeah, look at the second part. The second part is so special, so special. So how special it is? The subscript capital M in the exponent multiple of the same capital M. this structure, we can use it because based on the definition here, definition Wm, so we can see W capital M exponent capital M must be equal to 1. Okay, so 1. So this is actually the second factor is 1. So it's gone. Okay, it's gone. Yeah. Now you can see even. So here, although in the original formula, so here in the original formula, the little n can be in the second half range, but after our simplification here, we only need to consider little n in the first half of the range of the subscripts. Yeah, yeah. All right. So that's simplification. That's simplification. Okay. All right. Yeah. Yeah. So here, yeah. But another important simplification. We need to look at the factor outside the parenthesis. So the factor outside the parenthesis, the exponent, this time we need to consider m plus capital M. Okay? So with this n in the first half. First half. Okay? All right. So then for the little m plus capital M, then this in the second half. Okay? The sum is in the second half. Yeah. All right, little n in the first half, but after you plus capital M, it's in the second half. Okay, all right. Now we split again. This time we split again, and this time the second factor, because exponent is m, subscript capital N, based on the definition here and the 1/2 here, it's -1. Okay, so this factor equals -1. Because that's the e to the negative pi I. After cancellation, e to the negative pi I, it's -1. Okay? Yeah. So this e expression is -1. So that's the reason we have this negative sign, and that's the reason you see the negative sign here. Okay? So you see the negative sign here. Yeah. All right. So after this slide, you can understand how to derive these basic formulas. These basic formulas, okay? So this parenthesis point to this matrix expression, okay? So this parenthesis point to that matrix expressions, okay? Yeah, all right. So now we are ready. So after this slide, now we are ready for the next step. Yeah. So hope you can follow my explanation. Yeah. So it may not be very easy because too much details, too much computation details. So if you can handle, so that would be great. Yeah. Otherwise, if you feel too hard, you can skip it. Okay? You can skip it. Here, I just, for those students who really want to understand the details, then you can use, this explanation to help you understand. Because in our textbook, the explanation for this part too little. Okay, it skip it. Too many intermediate steps. Yeah. So here I try to help you recover those skip it intermediate steps. All right. So the next slide, here. Computation efficiency improvement. Now we are ready. Yeah, because only after you understand the previous slide, now we are ready to understand this slide. Yeah. The goal. So what is the goal? The goal is to show before the improvement, we have the asymptotic notation. So remember, I explained the meaning of asymptotic notation before. Okay, Yeah. So we need a capital O of n squared, now number of multiplications. Here we only look at multiplications because addition is much faster than multiplication. So basically, the time used for one multiplication equals 10 times of, for the addition. So 10 to 1 ratio. Yeah. So for that reason, so we want to focus on reduction of the number of multiplications. Yeah. All right, so here, the multiplication, the straightforward method. Yeah. If we do not do any special treatment, we will get n squared, constant multiple of n squared. Big O represent certain constant multiple of n squared. Yeah. Now, if we arrange our terms carefully and we try very hard to remove the redundancy, redundant computation. Yeah, because when you do computation, some steps you may do more than once. So we call it redundant computation. So if you have a lot of redundant computation, then the overall efficiency would be very slow. Okay? Yeah, very bad. Yeah. So we want to remove those unnecessary redundant computation. Yeah. So to make it faster. So our goal, we want to get this big O of n log base 2 of n. Yeah. That improvement is very big. Big improvement. How big? Last time I used 2 examples to show you the improvement. Yeah. Yeah, remember, the first example when n, capital N, equals 1,000. So then the ratio of improvement is 100 to 1 in ratio. Yeah. So the faster FFT would use 1/100th of the original time. 1/100th. Okay? Yeah. But the second one, even we can save more. The second one, we use, so let me write here. When capital N equals 1 million, yeah, so very large, then the response time ratio, 50,000 to 1, 50,000 to 1 ratio, that big improvement. Yeah. So if we can prove the improvement is like this, then we can derive, that impressive ratio. Okay? Yeah. All right, so now I explain how do we get that? Okay? How do we get this formula? Okay? In the textbook, it is not explained. Yeah, in the textbook. Yeah. So I try to recover. Okay? In textbook, it's hidden. Okay? So you only have the result. But the textbook actually show you a simple example. Try to let you see it. But that example is too simple. Yeah. That example is n equals 4. Okay? That number too small. So it's still too hard to see this formula. Okay? Yeah. So I searched the web and, a lot of articles, I couldn't find the good explanation on this part. Yeah. The formula is too complicated. So that's not good. Okay? So here, so I use my own digest. Yeah. So I digest this part. So now I show you my understanding here. Okay? All right. Yeah. So let's start. The goal, we want to calculate this vector, the frequency vector. Yeah. So remember, we call the frequency spectrum. Yeah. So here we write it in the vector format. Okay. Yeah. So and we want to remove redundancy. So as I mentioned. Yeah. So what kind of redundancy? Later, when I talk about the formulas, you will see the redundancy. Okay? Yeah. All right. So how to do that? First, I want to split this targeting vector. This is our targeting vector, yeah. Frequency vector. Yeah. Let me split it. First half and the second half. Yeah. Remember, the first half representation, the upper formula, the second half representation, lower formula. Yeah. So that means we should use this structure. First half, second half. And then we want to explore the duplicate computation. Yeah. The duplicate. Yeah. First half, second half, they are closely related. You can see these two formulas are closely related. Okay? And they may share a lot of duplicate computation. Yeah. All right. So let me split. Okay? The first half, then I draw this dot, 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 this line to separate between first half and the second half. Okay? Yeah. The first half is a vector, second half is also a vector, and they have the same dimension. Okay? Same dimension. That's the m-dimensional vector. First half, second half, both m-dimensional vectors. Okay? Yep. What's wrong? Yeah. Dimensional vector. All right? Yeah. All right. Then the expression of the first half, that vector, if you look at this formula is representation for individual component. Okay? Just one component in the vector, individual component. But let's put all those components together. Here we put all those components together, and we use the matrix formula to represent it. So you can get it equals the capital F sub m matrix times the even sampling vector. So this is even sampling vector. Yeah. So here, you're from this structure, so you can get that even sampling vector. Yeah. And this one from the previous slide, you can see the first parenthesis. Remember, we have two parentheses. The first parenthesis, you can get this one. Okay. Then the second parenthesis, you can get this one. The parenthesis part, you get this one. Outside parenthesis, it's this factor. Okay? Yeah. Yeah. So the vector, the matrix vector representation for the first half frequency spectrum vector, we have this representation. Okay? Yeah. Yeah. You just from the individual component to vector representation, do that interpretation. Yeah. All right. Then the second half, then we use the second formula here, and we use the matrix vector multiplication. So the only change we need to do, subtraction. Yeah. So these two matrix product, then the first one plus sign, second one minus sign. Okay? All right. Now, let us explore the duplicate computations. Yeah. So I talk about duplicate computations. So what's the duplicate computations? Yeah. Yeah. So look at the first matrix. When you compute the first matrix times a vector, you need to do certain number of multiplication, right? Yeah. But when you do the second one, do you still need to do the same matrix vector multiplication? You don't need, right? Because the first one, after you complete the computation, you save it in a temporary variable. You save it in a temporary vector variable. So the second one, you do not need to recompute it. Okay? You just retrieve from that temporary vector. Yeah. So you retrieve it. So you can save time. Okay? You can save a lot of computation. Okay. All right. Similarly, this second term, same, right? Yeah. So no computation the second time. All right? Yeah. So look at after we split into two halves, you can see the second half basically no new multiplications. Yeah. So here we use the idea we call reuse the resource. Yeah. So what is the resource? The results we compute and we put in a temporary variable we call the resource. Yeah. Because something useful, how do we understand a resource? Something useful we treat as resource. Yeah. Because these two intermediate results, they are useful. So they are our resource. Yeah. So we should reuse our resource. So the second time, we should not recompute the same two vectors, right? So we just retrieve from the temporary storage and use them to do the subtraction. Then we do not need to do any new compute multiplication. So that's the reason we save. Yeah, you can see we save 1/2 of the computation or multiplication, right? Yeah, yeah. So for the second half, there is no new multiplication, and that means we save the multiplication for the second half. Okay, so that's a lot. That's a lot. All right. Yeah. All right. And similarly, when you do the computation for the first half, can you split into two halves again to save another half, and all the way, always half by half? Think in that way, right? So that would be great. You can save a lot. Okay? All right. Yeah. That's the reason. The FFT allows us to save a lot of multiplications. All right. Now, in order to understand why we get this, this great improvement, so here I want to do some rigorous derivation. Okay? Yeah. So at this point, after the analysis above, now we are ready to do some rigorous derivation. Yeah. To do rigorous derivation, let me introduce a H function, capital H function, yeah. And to do calculation here. Let H function, H of capital N, be the function as the number of multiplications to calculate this frequency vector. So this is the frequency vector, the goal. Right? Remember the goal vector, yeah, for our Fourier, discrete Fourier transform. Yeah. All right. So that's the. So here we want to get expression of this H function. Yeah. So we define this function, and we want to derive a recurrence relation for this function. Okay. All right. So and we know by our formula, so matrix formula, matrix representation, the discrete Fourier transform. So this is the discrete Fourier transform representation. Okay, yeah, this one. So you can, we connect to DFT. This is the DFT formula. Okay, all right. Yeah. All right. That means when we do DFT of this multiplication, we need H of capital N number of multiplications. Okay, so that's the notation. So here gives us the notation. So we need to use it in our recurrence relation. All right. Next, to calculate. So remember, we split into two halves. So we need to use that structure, two-half structure, to, try to represent this h function. Right. All right. Because to calculate two halves, so here, two halves, we need to calculate this matrix vector product, right? Yeah. So look at here. We need to calculate the first matrix vector product. And when we calculate this matrix vector product, how many multiplications do we need? Okay. Can you compare the structure with that structure? Are they look similar? Structure-wise similar? F matrix similar, and the vector component also similar, right? Yeah. The size is different. The size, one is size m, another is size n. Okay? So when it is size n, the number multiplication we use capital H of n. But when we change to size m, naturally the number of multiplications we need is capital H of m. Yeah. Because here m corresponds to the subscript n. Here the subscript n. So we use the H of capital N. Okay? Yeah. So that's the connection. That's the connection. Okay? But this product is for the first term. And now we need to calculate also the second term. Okay? So another round computation. Yeah. But to calculate the second term, so we need to save multiplications as much as we can. Yeah. As much as we can. So we need to do another special treatment here. Yeah. So let me show you what special treatment. Okay. All right. So when we calculate this, because this one has one extra W factor, you need to do multiplication. Okay. Yeah. So you cannot save this multiplication. But to do that, then there is an important step. Yes, because you want to save multiplications. So we want to change the, we want to change the form of it. Form, okay? So here, I use this form. I multiply, because this is a scalar, right? This scalar. Scalar just one number, okay? Scalar. Just one number, okay? Yeah. So this scalar number, if we multiply here, is it equivalent as we multiply inside this vector first? Yeah, to get a new vector, right? Then we use this matrix, multiply that whole vector. In this way, we can save a lot of computation. Okay? In this way, we can save more than we need if we just do the scalar multiplication of that one. Yeah. So, actually, we're saying, actually, you need to know you should not multiply this two matrix first. Okay. All right. You should do this multiplication, then scalar the last, then you get the same number of multiplication. Okay. Yeah. Here I write this form in this way because we can apply this H function easily. Okay, in that way we can apply H function easily. Okay, all right. So now, when we write this form, this new form, then for this vector inside the parenthesis, we need n multiplications, right? Yeah, because the scalar we need to multiply to m components one by one. Okay, the vector FOD vector, there are m components. So the scalar number, we need to multiply all those components. So we need n multiplications. After that, we get a whole vector. Then we do this multiplication. Is that m function? So is that m function? Yeah, so here, the total number of multiplications, we need h of m, then plus that scalar multiplication, we need this m multiplications. So that's the total number of multiplications for the second half. Not the, sort of second term. Yeah, not the second half. Yeah. Okay, second term. Yeah. All right. Now, our recurrence relation is almost there. Okay, recurrence relation almost there. So, recurrence relation, capital H of capital N equals 2 times. Yeah, because 1 here, 1 here. So, total 2 times capital H of capital N. Then plus another one, M. Yeah, this is our recurrence relation. Okay. Then we need a base case. So base case, when the H of 2 equals 1. Yeah. H of 2 equals 1, you can see easily from this formula, because when H m here the size equals 2, when you split first half, second half, each one just one number, right? So you only need to do one W multiplication, because this part you don't not need to do. Here, this part no multiplication. Okay? Yeah? This part, so here, yeah, because that capital F just a matrix, 1 by 1 matrix. That's 1. Okay? 1 times anything, you don't need to do multiplication, right? So 1 times anything, you keep it. Yeah. So you only need 1 multiplication. That's why when the data size equals 2, you only need to do 1 multiplication. Okay? All right. So finally, we need to solve this recurrence relation. Yeah. All right. So here, so we have now the last step. I just show you what's the solution of this recurrence relation. So then we are done. Okay? All right. So then it's pretty simple. But we need to assume capital N is power of 2. Capital N is power of 2. Yeah. 2 to the P. Yeah. All right. Then P equals log base 2 of N. Okay? Yeah. Now we can solve. Yeah. So capital N divided by 2. So it's 2 to the P minus 1. Yeah. So let's plug into our recurrence relation. So we get this expression. Yeah. This expression, we want to change its form by division. So we divide both sides by appropriate number. That number is 2 to the P. 2 to the Pth power, like that. After simplification, so we get this expression. Now, it's easier to see, the result. Okay? Yeah. Because if we do another iteration, you can see we replace here, because it is true for all P, right? Yeah. So we replace P by P minus 1, so we get this formula. Then we replace this term by the right-hand side of the second equality. Okay? So that gives us, this time 2 over 2. 2 over 2. Let's do iterations all the way down to the last equation. All the way down to the last equation. Can we do the iteration? Keep going. This, iteration, keep going. Yeah. But when we reach the end, Yeah, we should get this plus what expression here, the second term. The first term, because we want to use the base case, this is the base case. Base case, that's this one. Okay? Yeah. So, but what is the second term? Yeah. Here, I tell you the way to find the second term. Okay? All right. So when you do iterations here, yeah, look at, so there is some property we can observe. So the property is, look at the exponent number p minus 1 plus the numerator 1. P minus 1 plus 1 equals p, right? Equals p. Equals p. Okay? All right. Look at in the second iteration, p minus 2 plus 2, yeah, p minus 2 plus 2 also equals p, right? Yeah. Also equal to p. Yeah. So here we call it, this concept we call it invariance. So this is invariance. This p is, it never changes, invariance. Okay? Yeah, this invariance property. So then the last term, 1 plus that numerator number, the sum should be p, so the numerator should be p minus 1. That's the way we figure out the last term. Yeah. Otherwise, we get lost. Otherwise, if we do not use this invariance property, we get lost. Okay? Yeah. So now we plug in the base case. Yeah. So we get it. The sum is p over 2. Yeah. P over 2. Yeah. Then the last step, we can write h of 2 to the p's equals 1/2 times p 2 to the p. Yeah. So we go back to the n expression. You can see we get a 1/2 times n log base 2 of n. Is that what we want to get? The capital, yeah, so here, yeah, you know, yeah, go back. Yeah. Is that the one, exactly the one we want to get capital